are from Group 4 to present the project of measurement and instrumentation. We are giving a task to design a virtual instrumentation system and analyze in time and frequency domain. We choose a hairdryer as our tool to get the data analyzed by using a DaisyLab software. The application of the hairdryer is contained with handle, motor, heating element, nozzle and diffuser. The hairdryer have a heating element while a little loud from fan generating sound. An adjustable switch button with low and high volume allow users to control the airflow intensity. Also, we detect the source sound wave by using a laptop microphone as a sensor.
Now, I'm going to introduce the sensor that we are using for our project. We are using a microphone. More specifically, the microphone that is attached to our computer. A microphone is a transducer that converts sound waves into an electrical signal. There are various types of microphones, such as dynamic microphones, condenser microphones, ribbon microphones, piezoelectric microphones, and carbon microphones. Microphones have various industrial applications. Among them are broadcasting and entertainment, telecommunications, and even automotive industry. The most common among all microphones is a dynamic microphone. As you can see, an anatomy of a dynamic microphone is shown on the screen. The dynamic microphone works using electromagnetic induction. Sound waves hit a thin diaphragm, causing it to move. The diaphragm is attached to a coil and is surrounded by a magnet. The magnet creates a magnetic field around the coil. The sound waves hitting the diaphragm move the coil, and the coil's movement past the magnet creates an electrical current. This current is the sound signal at the input. As you can see, there's a diagram of a basic microphone system shown on the screen. First, the sound signal enters at the input source, which is our microphone. The sound signal is then boosted using a preamplifier because its signal strength is quite weak. So we use an input gain to boost the signal strength. It's then moved to an equalizer, which is used to adjust the frequency response of the audio signal. This allows for fine-tuning. It is then passed through a channel level, which is an audio processor, which can be used to apply various effects or modifications to the audio signal, such as reverb or delay. And then we move to a mixer output. A mixer allows us to adjust the volume levels of each microphone, blend different audio sources, and control various audio parameters to produce better quality audio. The final stage is the output device, which is most commonly a speaker. This is the same system that is used in all our computers.
Hello and good day to everyone. Now I'm continuing for the chapter 3, which is methodology. So now, as you can see on the screen now, it is DaisyLab, and the other software that I use is Decibel X, which is on the phone to get the average reading for the FTL or PW reference later. Now we will set up the DaisyLab first. So first, we follow this reference as our system layout. So first we need to insert analog input. So where can we get it? So we go to the modulus, go to the input, go driver, and just click it and long click it, and we pull it into this side and we will become analog input. Now the second modulus we need is digital meter. So here is the first digital meter, and we directly stand by for the second digital meter. And now we need the formula. We go to mathematics, and this is the formula interpreter. And don't forget to do the copy input, so to connect the value. And now we need to hit the right button so that you can set. You also need to do copy input. Now we connect the menu. Now we're ready for the second row, ready for the YT chart. So we need YT chart first. Just click it and drag it. The term name is data window. Go to analysis, and this is data window, and this is the FT. So just click, select this real FT of the signal. Then we need to insert the second YT chart again. Now, to set as a digital meter, we need to copy it. Now we connect the wire. Now we have done the layout. Now we move to the unit. So this unit, for this unit, we need to put D. So we need the volt. Now second we put dB, and decibel for the frequency part. So now I will show you the layout from our project. This is just a step at how to do the layout. So this is the layout from our project. Now I will show you. I will play this, and then I try to talk. You can see the wave will appear on this YT chart and the second frequency chart. So while I'm talking, the frequency will be reading, and it will show the reading at the chart here, and the value also will be appear here. This is V, this value, and this is dB 0. It's still 0 because the formula is 0, and we doesn't input the value yet because we need to find the formula from here. So we have done the experiment, and this is the step. We start hair dryer, solve the DZ and disable X as I told before, and make sure there is no interaction of other sound resources. Then we turn on the hair dryer as if near the laptop. Then we run both DZ and disable X, which is on the phone also, we run at the same time. And when the sound is steady, then we just pause at any time, then we take the reading. So we get the value, we can do the calculation. So the formula given is dB equal to 20 VRMS divide V reference. So this reading is from a decibel X to the average reading. So start in here. So we do the calculation, and we get V reference equal to 9.463 times 10 power negative 6 volt. Then we start that into the formula before. So we will have the formula 20 log input 0 divided by 9.463 times 10 power negative 6 volt. And we just copy this video. And then we type in our DZ formula. So that's all for me. Thank you.
Okay, now I will explain the process of the experiment. The equipment that we use is a hair dryer, a stopwatch, a sound meter apps which is Decibel X, and the DaisyLab software. Okay, before we conduct the experiment, we have to ensure that there is no interaction of other sound resources. And first, we will turn on the hair dryer and put it near the speaker of the laptop, together with the sound meter apps. Then we will, in order to measure the IMS value and the dB value from the sound meter apps. The experiment will be conducted for 30 seconds. And now let's start with the experiment. Okay. Okay, here is the IMS value that we get from the DeciLab, and here is the average value of the dB value that we get. Then we will put both of the value into the formula in order to get the voltage reference, and then the voltage reference will be used to conduct the equation of SPL. After we get the formula and we insert the formula into the formula interpreter in the DeciLab software, then we will do the experiment again in order to get the dB value. Okay, the experiment will be sent as before. Now let's start with the experiment. Okay, 1, 2, 3. Okay, and here is the graph, that time domain graph that we get in the DaisyLab, and here is the frequency domain graph that we get in the DaisyLab, and here is the dB value that we get. Okay, our process experiment ends here.
In a conclusion, we get some knowledge on how to use the DaisyLab software to analyze the sound wave data. We'd like to explore more about it because of the software are friendly user, especially for the first time user. The software are straightforward and uncomplicated to understand. We can know the function, setting, and arrange until we get the data collection. We fix a problem and find a solution during measure several sound frequency for this task. The DaisyLab show a simple meaning icon and model browsing, but the software are described in a block diagram. That's all from Group 4 presentation for Measurement and Instrumentation project. Thank you.